Hello everyone, my name is Bosun Kang and I'm undergraduate student majoring computer science engineering at Seoul National University. Today I'll be presenting our work titled Learning-Augmented Skill Rental with Discrete Distribution, a Bayesian Approach. This is joint work with Hejun Park and Professor Cheng-Li Fan at the Algorithm Foundation of Data Science Lab at Seoul National University. In this talk, I will explain how Bayesian reasoning gives us a simple yet robust decision rule for the classical ski rental problem and why this rule turns out to be surprisingly stable even when our prior information is imperfect. Let me start with a brief overview. First, we try to revisit the classical ski rental problem from a Bayesian perspective. Instead of ignoring structure in the horizon, we try to model the uncertainty using the prior distribution. And then we try to show the optimal Bayesian decision depends only on the survival tail mass, not on the exact shape of the distribution. This gives a clean explanation for why the policy is robust. Finally, we provide the systematic robustness study on the prior uncertainty, including errors in the mean, variance, and even model class, which shows a stable performance across large total variation distortion. At the high level, this work is about decision-making under uncertainty. The Bayesian framework is particularly natural here. We start with a prior belief about the unknown quantity. In our case, it's the usage horizon. As the time progresses, we try to update the belief based on what we observe, and then make decisions that minimizes the expected cost under the posterior. The key components are the prior, the evidence that we receive over time, the posterior belief, and the final decision rule that chooses the cheaper action in expectation. The ski problem is classical online decision problem. At each time step, the agent chooses between renting at cost 1 per day or buying once at cost B. The challenge is the total usage horizon T, which is the unknown in advance, right? In the worst case setting, the optimum deterministic strategy buys at the time B, while the best randomized achieves a competitive ratio of about 1.58%. However, this is completely ignores the prior structure and the unable adapt to realistic usage pattern. So, in our Bayesian formulation, we try to assume the prior distribution over the horizon T. A key object is the survival function, which represents the probability that usage continues to beyond time T. Conditioning on survival, we compute the posterior distribution of T given that we have reached time T, which allow us to evaluate the expected remaining rental cost from any point in time. The Bayesian rule is very simple. At each time step, we compare the buy cost B with the expected remaining rental cost conditioned on survival. If buying is cheaper, we buy. Otherwise, we keep renting, right? This comparison introduces the threshold structure. There is a first time T at which buying becomes the optimal, and before that, renting is always better. The key difficulty comes from the unknown horizon. In the worst case analysis, we try to concentrate all the probability mass at a single bad point. But in real world, horizon looks very different, right? Then they can be even bimodal, seasonal, skewed, or heavily tailed. A Bayesian algorithm must reason about this full distribution structure, not only the single worst case scenario. So the main challenge is sensitive. Even a small change in the prior distribution can significantly alter the survival curve. And since the threshold depends on this survival, this could be leading to very difficult decision. So it really raises the natural concern. Is Bayesian ski rental fragile to prior misspecification? And let's see if it's actually really considered the problem. On this slide, I'll try to introduce my Bayesian model. We try to assume the discrete prior distribution over the unknown horizon t, right? Which is written at pi of k, which means the probability that t equals k. From this prior, we define the survival function s of t, which equals the probability that t is greater than or equal to t. Mathematically, it is the sigma from k equals to t to m of pi of k, meaning we try to sum all the probability from time t onward. This survival function is the key quantity used for decision making. Then we try to compute the expected remaining rental cost. At time t, we try to consider the expected value of the minimum of t minus t plus 1 and b, which is given that t is at least t. In words, this means that either the usage ends soon or it lasts long enough that renting would cost as much as buying. The single expectation captures the both cases and allows us to compare the renting versus buying in expectation. From this comparison, a clean threshold structure emerged. The Bayesian policy buys at the first time t such that b is less than or equal to expected remaining rental cost at time t. Before this time, renting is cheaper in expectation. After this time, buying becomes cheaper, which gives us a deterministic and monotone threshold once the prior is fixed. And here's the algorithm that I have made. In the pre-computation step, we first compute S of t, the survival probability, right? Then we compute the tail expectation as mu of t, which sigma over tau greater than or equal to t of tau minus t plus 1 times pi over tau divided by S of t. Online, the rule is very simple. If the current time reaches the threshold, we buy. Otherwise, we continue renting. Then we'll try to move on the experiment to test out. In experiment 1, we studied the robustness under prior misspecification. We start from ground truth distribution called pi star, meaning the true horizon distribution. Then we construct distorted priors called pi-tar, introducing errors in mean, variance, or shape. We measure the performance using cost increase, competitive ratio, and failure rate. The results are very strong stability. Even when the assumed prior is heavily distorted, the average cost increase is only about 5%. The worst-case degradation occurs mainly under large mean shift and remains below 20%. Errors in the variance or shape have almost no impact on the performance. This result can be explained by the threshold that is determined. In the most case, the expected horizon E of t is larger than the buy cost p, which decision depends mainly on the survival function S of t, not on the local feature of the prior distribution. As a result, moderate misspecification does not significantly change the buying time. In the experiment 2, we try to study the robustness to the prediction noise. We begin with the predicted prior. Pi hat produces the forecasting model. Then we inject the control noise by scaling and perturbing the prediction. The Bayesian policy is compared against deterministic ski rental, randomized ski rental, and the point prediction base. Then, our Bayesian approach consistently achieves the near optimal performance. The mean comparative ratio stays around 1.02 across all noise levels. The success rate, meaning a valid threshold, is computed. which is about 98.7%, right? In contrast, classical strategy degrades significantly as noise increases. So, on the other hand, experiment 3 tries to focus on the model's misspecification. Again, we start with a true distribution, pi star, and construct distorted priors, which is pi tau, right? The distortion level is measured using the total variance distance, which quantifies how different the two distributions are. Decisions are made using the distorted priors, but costs are evaluated under the true one. And the key result that is very simple. Even under severe model misspecification, performance remains very stable. The average cost increases is small, and the worst case degradation is limited. The stopping threshold remains stable because it depends mainly on the expected horizon E of t, right? And the survival probability S of t. In the experiment 4, we try to test the multimodal horizon distribution. For example, a bimodal distribution is 0.7 times a normal distribution with mean 10 and variance 9, plus 0.3 times a normal distribution with mean 25 and variance of 25. We consider trimodal and seasonal distribution as well. And the key finding is that multimodality does not affect the decision. The algorithm does not respond on the peak in the distribution. Instead, the decision is governed entirely by the survival function S of t, which is the monotone. Therefore, the number location modes does not change the threshold. One important feature direction is the learning prior from the data. Our current approach assumes a handicraft prior pi, but real-world horizon distribution evolve over time and can be noisy or even seasonal. Automatically learned priors will be allowed threshold to adapt dynamically, right? Another extension is to multi-resource setting. In the problems, buying one resource can affect the cost of another. This introduces interacting threshold and the multi-dimensional posterior updates, which remains one opening challenge as well. So to conclude, our Bayesian skill rental leads to a simple threshold policy that is both theoretically grounded and empirically robust. Even under this uncertainty and the prior errors, performance remains stable because decisions rely on the global survival property rather than the local details. Thank you for your attention.